Hello and welcome to this recorded e-learning on Spartan-3 HDL coding techniques. This module is one of the recommended recorded e-learning modules for the Designing for Performance course and is also a part of the FPGA to ASIC REL curriculum. My name is Frank Nelson. I will be your instructor for this module. I am a Xilinx technical trainer and course developer. This module introduces some of the architectural differences of Spartan-3 and their impact on HDL coding techniques. This module introduces some of the primary concepts that impact the quality results a designer will get when synthesizing for a Spartan-3 FPGA. This module also provides some detailed recommendations about creating effective HDL that will provide high speed and reduce the amount of FPGA resources used in your design. This slide describes the curriculum path for ASIC designers to learn Xilinx software, hardware, and FPGA design techniques. There are 5 RELs to help you get familiar with FPGA design. There is also a corresponding HDL coding techniques module for Spartan-3 devices. The content in this module will help you immediately start making coding improvements to your Spartan-3 FPGA design. There are 2 modules for Spartan-3 HDL coding techniques content. This is part 1. For more information on these courses, visit support.xilinx.com and click on the education link at the top of the page. Also note that these RELs do not introduce the ISE design suite, good design practices, and other essential information. This content is part of our Fundamentals of FPGA Design course and the Designing for Performance course. We recommend that you take the time to attend these courses if possible. After completing this module, you should be able to build efficient Spartan-3 FPGA design that has an efficient size and runs at high speed. We're also going to show you how to avoid some of the most common design mistakes. This content is essential if you have never coded a design for any 4-input LUT architecture or are converting an ASIC design. Our goal in this module is to try and teach you some of the subtleties of the Spartan-3 FPGA devices. To pack the most logic into your FPGA sometimes takes some optimization of your code. Likewise, to get the required design speed sometimes takes further optimization. We should note that designers do not always have to follow these tips to meet timing, but they should still follow our recommendations because these tips will lead to significant design improvement. As you probably know by now, synthesis tools do not allow for inference of all FPGA resources. Sometimes good coding techniques are required just to get an optimum resource into your netlist. While the content in this module is not specific to a particular synthesis tool, and some of the tips have not been tested on all synthesis tools, this module does provide a good basis for experimenting with your own synthesis tool. This module is recommended content for the Designing for Performance course. I recommend again that you take the time to consider taking that course, and come to the class with questions on the content you're about to learn here. The content in this module also applies to any 4-input LUT FPGA device family. This includes the Vertex 4 family of FPGAs. There are corresponding RELs on Vertex 5 HDL coding techniques that discusses some of the issues with design conversion and proper coding for its 6-input LUT architecture. We are going to discuss some of the most important ways to optimize your HDL code for Spartan-3 FPGA. After listening to this entire module, you should be able to make your own checklist of tips for building a high-speed Spartan-3 design. We first want to point out that the information we are going to present serves as a solid set of guidelines. We do believe these tips will very often give you the best result, so we encourage you to start with what we instruct, then experiment on your own. These design practices will improve your device utilization, speed, and reduce the cost of your finished design. These tips can reduce the size of your design by 20% or more. And if your design is so much smaller, it can fit into a smaller device, which will save you a significant amount of money. Likewise, your design will implement faster since the tools have more freedom to place logic and meet your timing constraints. Likewise, since the tools have more flexibility to meet your timing, they can get your design to run at a higher operating speed. So by following these tips, you are free to run small, run fast, and run at a low cost. Well, this is the Spartan-3 slice resources. As you know, each slice contains 2 LUTs. Each LUT can handle up to 4 inputs and generates 1 output with constant delay. The carry logic resources are used to build fast arithmetic operations. They are dedicated logic and include a dedicated routing resource. These resources are extremely fast because the routing is fixed and is not programmable. Each slice has dedicated muxes. Specifically, the F5, F6, F7, and F8 muxes were added to enable you to build larger multiplexers that are fast and save lookup tables and routing resources. Recall that before these dedicated muxes existed, a large mux would be built with just lookup tables. This would run slow because of the extra levels of logic required. This is, of course, no longer the case. These muxes have dedicated routing that is also extremely fast and fixed. Each slice contains 2 flip-flops that have dedicated set, reset, and clock enable ports. This provides a significant amount of flexibility. Note that the set and reset must both be synchronous or asynchronous. We will talk more about this requirement a little later on. As you know, one of the recurring themes in FPGA design is to target as much of the dedicated hardware as you possibly can. This is especially true of the block RAM and the DSP slice resources, which are abundant. Using these resources saves LUTs and registers for other purposes. And since LUTs and registers are the most flexible resource, this always means that we can pack more logic into the FPGA and get more for the money. So wherever possible, we encourage our customers to think outside of the box and come up with creative uses for the FPGA dedicated hardware resources. In fact, this kind of product feedback is exactly what we look for when we are planning a new product. A LUT can implement any function of up to 4 inputs with only 1 output. It does not matter how complex the logic function is. In this case, we see a simple mux of 2 inputs being made. This, of course, fits nicely into a single LUT since it has only 4 inputs, that is 2 data and 2 select lines. However, when a designer only uses 2 or 3 inputs, he is leaving money on the table since he is not using all of the LUT's capabilities. Keep this in mind. It cannot often be helped by the designer since he only cares about the desired functionality that he needs for his application, but understanding that the inputs are limited helps you appreciate some of the common mistakes designers make when targeting an FPGA. In this case, the designer wrote HDL to behaviorally describe the mux, and the synthesis of the logic and the mapping to the Xilinx primitives, that is the LUT4, was done by the synthesis tool. Remember that the synthesis tool's primary output is a netlist that references the FPGA primitives. The implementation tools do not do any optimization of the design's combinatorial logic, so you must learn to work with what your synthesis tool gives you, which is an optimal synthesis. The best way to estimate the size of a function is to check the synthesis results with the available reports and the schematic viewer provided by the synthesis tool. The combination of the interconnect delay and the LUT delay forms a single logic level. In this example, we have 3 levels of logic. The critical path delay is about 8.9 nanoseconds in this example, of which 7.4 nanoseconds is made up of interconnect delay. This may or may not be typical for you, since internal delays will of course vary by family and speed grade. But in our case, we're just going to work with this for an example. Always keep in mind that your synthesis tool will decide how your logic equations will map to the LUT architecture. So it will decide how many LUTs and how they are connected together. So depending on your coding style, the synthesis tool might choose to code some logic in series, as in this example, but depending on the type of component you're building, your synthesis tool might be able to build that logic in parallel. Fortunately, synthesis tools are getting better at mapping logic to parallel LUTs. The delay associated with the LUT is also very small, less than 0.5 nanoseconds typically. However, at the design level, it can appear that performance is highly variable, and you should appreciate what causes this to happen. The number of LUTs you have in series may be high, and thus the total delay on a critical path may be too long. The routing delays with the newest devices are nearly equivalent to LUT delays, not quite as in the case of this example. In fact, many of us use this way of estimating timing. We call that the 50-50 rule, where half your delay is routing and half your delay is logic. Each time the logic maps into multiple logic levels, you simply add more connection delay. So the delay increases in steps each time you exceed 4 inputs. If you could somehow always build logic with 1 LUT delay, you would be operating at peak performance or very high speed. You also should know that the implementation tools can try to place logic closer together in an effort to shorten your net delays. So here are a few things you should remember about coding styles for lookup tables. First of all, try to maximize the number of inputs to each LUT so that you can obtain the most logic out of the FPGA. Also, instantiate the appropriate LUT primitive if necessary, and if you want to learn more about LUT primitives, you can refer to the Xilinx Unified Libraries Guide. This is provided for you when you install the ISE software under the Help menu, and then you go to Software Manuals. Or if you want, you can go to support.xilinx.com and you can go look for the Xilinx Unified Libraries Guide there. A logic level is 1 LUT plus 1 net delay. So whenever we talk about multiple logic levels, we're talking about multiple nets and multiple LUTs cascaded in series. Synthesis tools in your coding style will often determine how many logic levels there are in every path of your design. But this, of course, will vary. But we're going to look and try to highlight in this presentation a number of cases where the coding style is pertinent. As this slide shows you, originally when you built a 4-to-1 Mux in an older device family, the Mux was built entirely of just the lookup tables. In this case, a 4-to-1 Mux would use 3 LUTs and be built with 2 logic levels. Pretty good performance, but as you make the Mux larger, the delays will increase quickly, and you'll end up with multiple logic levels and hence slow performance. With the newer device families, you have access to the F5, F6, F7, and F8 Muxes. These are used to build 4-to-1, 8-to-1, 16, and 32-to-1 Muxes, respectively. In this example, we use the Mux F5 to group the outputs of the 2 LUTs in the same slice to make a 4-to-1 Mux. This gets better speed than the older implementation because a LUT delay and the routing delay between the Muxes is saved. In this case, it uses 2 LUTs and uses 1 logic level, better than our original result on both counts. So by using these Muxes, you save LUTs and get better speed. Wow, win-win scenario. Remember that this requires the 2 LUTs associated with the F5 Mux. You can't just group any lookup tables in this fashion. Likewise, there is dedicated routing associated between the other Muxes to create the faster and larger multiplexers. So you can't just separate these resources out. You have to use the ones associated with a single CLB. Finally, be sure to use your schematic viewer to make sure that your synthesis tool infers these resources correctly. Although the primary use of a Mux F5 is in creating larger multiplexers, it can also be used in the generation of any logic function of up to 5 inputs. The connectivity between the LUT and the Mux F5 means the 2 16-bit truth tables associated with each LUT are concatenated to form a single 32-bit truth table. Note that while Mux behavior can be inferred in most cases, it will require the use of a case statement in your HDL. The Mux F5 can implement some functions of up to 9 inputs, providing the inputs can be separated into 2 functions of 4 inputs. Unfortunately, not quite as useful as you might think. However, this will require you to instantiate the appropriate Mux primitives to construct your system in this way. This slide shows how the F6, F7, and F8 Muxes can be combined to create 8-to-1, 16-to-1, and 32-to-1 Muxes, respectively. Because the F5, F6, F7, and F8 Muxes can be inferred automatically by all the high-end synthesis tools, most designers do not instantiate these resources. However, a case statement will be required. You should also note the specific sizes of the Muxes that can be made with each of the dedicated Muxes. The F5 requires 2 LUTs in 1 slice. The F6 requires 4 LUTs and 2 different slices. The F7 requires 8 LUTs and 4 slices, or 1 CLB. And the F8 requires 16 LUTs in 8 slices for 2 CLBs. And of course, as I mentioned before, all of these LUT combinations are fixed. You can't just pick and choose which LUT's going to be combined. In this exercise, see if you can build the Muxes that we're describing here. These are not quite as easy as you might think, but take a few minutes and draw it out. In fact, I encourage you to refer to the last couple of slides about these resources. Calculate how and which type of Muxes will be necessary to create these. So we have, first of all, on the left-hand side, we have a large multiplexer with 8 inputs and 3 select lines with a 12-bit output. On our second multiplexer, we've got 5 inputs with 3 select lines and a 12-bit output. So grab some paper, pencil, and have some fun with this. Spend a few minutes and then come back and you can look at the answer. Well, the first question, which is the 8-input, 3 select line, 12-bit output multiplexer, can be thought of as being an 8-to-1 mux replicated 12 times, since it has a 12-bit output. Now recall that the 8-to-1 mux uses 4 LUTs plus an F5 and an F6, which equals 2 slices. So the entire mux will be that configuration, okay, times 12 for 12-bit output. It also is extremely fast, since each of the LUTs are in parallel and the delay of the F5 and F6 muxes is almost negligible. The delay is just one level of logic, and that's pretty amazing when you consider that previously this would be just built with LUTs in series. Multiple levels of logic and get horrible performance. But now that you get the dedicated muxes, it just flies. Well, the next question we'd asked you, which was the 5-to-1 multiplexer with 5 inputs, 3 select lines, and a 12-bit output, has got a couple of different possible solutions that could be found. And they're not quite as easy. So you probably didn't get these right, and if you didn't, don't worry about it. Okay, so like I mentioned, there's going to be 2 solutions, and indeed XST may use either, depending on the coding style and the synthesis options you select. First, you see that the 8-to-1 multiplexer can be stripped down to use fewer inputs, but to reach the Mux F6, you have to use parts of the other slice just to route to the 5th data input. Now that's a problem because, of course, we do run the risk of wasting lookup tables if we start using the dedicated Muxes. Although one LUT is left unused, the structure must use 2 slices per bit and will force the design to be spread out. The great advantage of this answer is that it is still one level of logic, which is high performance. The alternative, which is in the lower area here, is to decompose this mux into a 4-to-1 multiplexer followed by a separate 2-to-1 multiplexer. They could be in a different order, but that could make the select lines harder to drive. Notice that while this is smaller and would pack nicely, the delay will be greater due to the 2 levels of logic and the general interconnect wire. So here's a tip. If you have a big multiplexer and intend to break it down into sections in order to pipeline it, try to work with units of 2, 4, 8, and 16 inputs each time. So for example, break a 12-to-1 mux into an 8-to-1 and a 4-to-1, not into 2 6-to-1 multiplexers. So anyway, I hope you enjoyed the exercise a little bit. They're pretty challenging, especially the second one. But as far as I'm concerned, if you could get the first one, then you've got a good idea how these muxes are done. And in the real world, as I mentioned, you're going to be coding this in HDL and synthesizing. You're probably just going to go with that result. So here are a few things you should remember about coding styles for the dedicated muxes. So the F5, F6, F7, and F8 muxes build large, fast multiplexers, as you know, and these resources are fast, built-in dedicated logic with fixed routing. To infer these resources, you'll need to use a case statement in your HDL code. And you can always verify with your schematic viewer provided by your synthesis tool that you actually were able to infer these dedicated muxes. And this is a standard exercise I tell everyone should be doing. Verify that you're getting the correct Xilinx primitive map to your netlist, and that's the easiest way to do it. Look at the schematic viewer. Inference of unique functions will probably require instantiating the appropriate multiplexer primitives And if you want to learn more about those primitives, and they're pretty basic, go to the Xilinx Unified Libraries Guide. I think I mentioned to you before, you can get access from your IC software or go directly to support.xilinx.com. We also recommend to break up a large multiplexer down into smaller sections for pipelining. You might want to consider to break them up into increments of 4 and 8. Okay, so don't choose odd numbers like 6. Make it into 4 and 8. It works better with the dedicated Muxes. Current FPGAs have a clock-enabled set and a reset port on the flip-flops. All can be locally inverted, and the set and reset ports can be programmed as synchronous or asynchronous on the register. You should especially note that they both must be synchronous or asynchronous. You cannot mix and match. To code for these resources, you must follow the device priority of reset first, set second, and clock enable third. Keep in mind that your HDL code must follow the same order of precedence if you're going to be able to infer the control signal ports on the register. The benefit of using these ports is that the corresponding behavior does not have to be programmed into the LUT resources. Thus, this saves LUT inputs and increases the amount of logic that a designer can get out of the FPGA. It is very important that you follow good synchronous design practices. This means that you must make all of your local resets synchronous, and even better if your global resets are synchronous as well. If you don't, your design might glitch, and that's a problem you don't want to debug later. With so much control signal support on the register, one of the common mistakes is that the designer doesn't manage the number of control signals their design has. When a designer adds a core to the design, they might infer a different control signal and then not share the control signals throughout the design. This kind of mistake can reduce the ability of the designer to pack logic into the same slice or CLB. So sometimes designers have to go back and reduce the number of clocks or control signals they have, since they also can run out of global routing resources or even create routing problems by using general interconnect for the distribution of these control signals. In this example, you should note how the priority of the control signals is followed with its HDL coding. This assures that the control signals will be mapped directly to the register and not waste a LUT input. So the reset comes before the set, and the clock enable is listed last. And also note that the reset and set in this example are both synchronous, which is good for good synchronous design and avoiding glitches. As part of following good synchronous design practices, you should never gate an internal clock. In this example, a counter is decoded and the output is directly connected to a clock port. Leaving a gated clock in your design is a big risk because the generated clock can glitch. The resolution is very often essential. In fact, if it is not done, it is usually fixed during debugging of the design. To fix this problem, we connect the decoded output to the clock enable port of the register. To infer this, all you have to do is connect the decoded port to the flip-flop's clock enable port, as we will see in the next slide. On this slide, we see the Verilog code to infer the clock enable signal that we just saw on the last slide. All you do is decode the output by checking for the count to equal a value, and then assign the D input to the Q in that case. So don't forget, never gate a clock. All local sets and resets should always be synchronous. Otherwise, you will build a glitch into your system in any FPGA. An asynchronous set or reset creates the same problem as a gated clock, and this design mistake will propagate erroneous data, which can appear random. To make a set or reset synchronous, all you need to do is make sure the set or reset signals are not in the sensitivity list, as we will see in the next slide. So as we see in this example, the synchronous reset is nested as part of a clock process, and the reset signal is not in the sensitivity list. So the only way this circuit will get reset is if the clock signal is already on the rising edge. Since we have coded for the reset port and not violated the priority of the control signals, the synthesis tool will infer the appropriate primitive and connect the reset port directly to the register. Control inputs to the flip-flops have a predictable priority. This can be reviewed in the Xilinx Unified Libraries Guide, or can be directly interpreted from the primitive names for the flip-flops. The name of the flip-flop tells us the priority of the controls and not just which controls are available. So in this case, we see we are using an FDRSE primitive from the Xilinx Unified Library. The F stands for flip-flop, of course, and the D defines the type of the flip-flop. The R defines the reset as having priority over all the other control signals associated with this flip-flop. This also means that the flip-flop will be initialized to 0 after configuration by default. The set, or S, comes next and has priority over the remaining control signals. Lastly, the clock enable has the lowest priority. Another common question is, how do you define the initial state of the flip-flop after configuration has occurred? In this case, since the synchronous reset has the highest priority, Q will be 0 after configuration. But this is programmable by using the init attribute in your UCF file. For more information on this, refer to the Xilinx Unified Libraries Guide. This can be useful if you want to remove a global reset signal from your design. This would give the tools more flexibility to meet your system timing objectives. It is also important for you to not mix synchronous and asynchronous controls on a single flip-flop. This is not supported and will force the synchronous control signal to a LUT input. This is because the synchronous control signals can always be routed to a LUT input to get the same result. Asynchronous control signals have no choice but to be connected directly to the appropriate port on the register. So mixing control signal types will waste LUTs in the long run. It has become a very common practice in HDL design to include a global reset. It is often taught in coding styles and shown in many examples. One of the main driving forces for including this global control signal is for simulation purposes, so that there are no unknown states at the start of a simulation. Well, FPGAs don't have any unknown states, so using a global reset is unnecessary for simulation. We'll talk a bit more about this in a moment. So you first must consider that if the global reset is asynchronous, which most are, it will force the flip-flop control ports to both be asynchronous. So any synchronous control signals, that is the set or reset, that you have in your design, if they're used on this circuit, will now be forced to a LUT input. The use of the global reset can also steal the use of the reset port from a local reset. This forces the tools to again use a LUT input if the control signal is synchronous. A global reset will use a lot of routing and have a high fan-out leading to potentially long delay paths and skew. Having excessive skew and not making your reset synchronous can lead to non-reliable operation as different flip-flops are released on successive clock edges. The point is that you should not be increasing the size of your design to fix a simulation or coding style issue. This is often a problem for ASIC designers since global resets are frequently included. In this example, the design has an enable, an asynchronous clear, and a synchronous set control signal. To understand how this gets mapped to the FPGA, you just have to remember the rules about register control ports. So in this case, the asynchronous clear must get mapped to the reset port of the flip-flop. There is just no other way to connect the reset without losing its asynchronous quality. This then forces the set port to also be asynchronous, and since the set is synchronous, it is then forced to a LUT input. This will waste one LUT input to every register that has the synchronous set. That could end up to be a lot of LUTs. It will just depend on your design. Likewise, since the synchronous set has to resolve its priority with the clock enable must also drive a LUT input. So after all is said and done, two control signals are now sucking up half of our LUT inputs, and we are routing 3 possibly high fan-out control signals on general interconnect. This could suck up some routing and make it a bit more difficult to meet our timing, but again, that will depend upon the size of this component. The moral of this story is, don't mix asynchronous and synchronous sets and resets on the same flip-flop. If we make that change, we can map all the control signals to the flip-flop. Now, as we mentioned, you can save yourself from routing a global reset if you understand that the flip-flops come initialized to a known state after configuration. This defaults to 0 or can be initialized to 1 if you use the init attribute. Likewise, initializing your registers in your HDL will enable you to test your design in that same known state. Just take the time to write proper behavioral code, as we can see from our example. This is pretty basic. If the design functions during simulation, we should know that it should function in the FPGA. So simulation is still strongly recommended. In this slide, you can see how much fan-out a typical reset can have. This is probably the biggest reason to remove resets from your design, since all of these routing resources will be available to the rest of the design to help meet critical timing and increase device utilization. Since resets use regular routing resources, saving this routing allows the tool significant added routing flexibility to meet your critical timing needs. You should remember that the Shift Register LUT, or SRL component, does not have a reset port. So if you have a reset on the shift register in your code, the synthesis tool is left with one or two choices. They either do not add the SRL primitive to your netlist, meaning they end up using a bunch of registers, which will of course increase the size of your design and is simply not what you want, or they can try to emulate the reset. Emulating the reset means that your synthesis tool can add more logic and the design becomes even slower than it should be. Note that only Simplify currently can do this. XST currently cannot do this. You should also note that the SRL can easily be inferred when you build synchronous FIFOs, non-binary counters, terminal count logic, pattern generators, and reconfigurable LUTs. So not inferring a reset in your design, that is a global reset, would infer more SRLs and save a lot of registers each time. In one customer design, there was a global reset through everything and the known shift registers could not be connected. They in fact were inferring 100 SRLs and were doing a good job making good use of the dedicated hardware. But by doing a redesign and removing the global reset, they obtained over 150 shift register LUTs. The customer obtained even more shift registers than were initially recognized. Those 50 SRLs saved hundreds of registers and improved the overall speed of the design. This is just a short list of some additional reasons that why we should not build a global reset into our design. But the big one is the first one listed. Meeting your timing objectives is simply a lot easier when your design does not have a global reset. In fact, performance improves by an average of 18%. No reset also speeds your implementation time and allows the tools to use less memory during place and route. But one thing that is important to understand is that synchronous reset paths are timed by the implementation tools. That means that their paths are covered when you use global timing constraints. But your asynchronous reset paths are not covered by global timing constraints. So using a synchronous reset in your design increases the number of paths. But your confidence in your design operating properly and the static timing analysis being accurate goes up significantly. So if you can't remove your global reset, it is still smarter to make it synchronous. So here are a few things you should remember about coding styles for your register resources. First of all, try to manage the number of control signals in your design. And as I mentioned, if you start instantiating cores or using older netlists, make sure that those control signals are shared with the rest of the logic you're building. All three control ports on the register can be used. To directly use the pins in the register, the priority, of course, must be reset, followed by set, followed by clock enable. Be careful to never gate your clock. It will simply not operate reliably. Instead, map this functionality to the clock enable port if possible. Do not build with an asynchronous reset. It will not operate reliably again, especially if it is local. Global asynchronous resets might work, but it might waste LUTs and create a long net delay, which is of course a big caveat to their use. Do not mix asynchronous and synchronous control signals on the same register. And do not use a global reset to make simulation easier. Simply initialize your registers in your HDL. The SRL allows you to emulate a 16-bit shift register with one LUT. The shift register LUT does not support the use of a set or reset. It is also serial in and serial out only. No parallel read or write. So don't expect to read the contents at one time. It is basically a delay element. After data is loaded into the SRL, the data appears in the output a number of clock cycles later, which you control. You should also remember the dedicated flip-flop next to the LUT has a better clock-to-output time than the SRL, so consider adding this register if you need better performance. The initial contents of the SRL can be specified with the init attribute, or it will default to a 0 initialization. The benefit of the SRL is that it saves users from having to add registers to balance a pipeline stage. Frequently, a designer will have to use registers merely to delay a data path, so it balances with other data paths. A designer might end up using 4 registers on each bit of a 16-bit bus to balance a pipeline, for example, and that would normally require 64 flip-flops. But by using the SRL, a designer can instead use 16 LUTs to do the work of 64 flip-flops, a nice saving of the dedicated resources. In this case, the connections to the LUT inputs assign the number of clock cycles of delay, and in this case, 0100 corresponds to 8, and that's attached to the address lines and will effectively make the LUT behave like a shift register with 8 clock cycles of delay. Synthesis tools such as XST will automatically use this feature as long as it is coded properly. So don't code for a set or reset functionality, otherwise you'll infer the actual registers and not the SRL primitive. Here is some simple HDL showing 16-bit data being delayed by 5 clock stages, which would normally require 80 flip-flops for storage. But note that a global reset is being used. This will effectively prevent us from inferring the SRL, and we'll end up with 80 actual registers being wasted. If you remove the reset signal, it will use the SRL and you will save all those flip-flops. When we synthesized this with the reset, we got the following warning from XST. As you can see, it recommends removing the reset functionality if possible. So this will teach you to not read the warning messages provided by your toolset. So here are a few things you should remember about the coding styles for the shift register LUT. So the SRL, again, is an effective means of delaying a data path. It's not an actual shift register. But in its implementation, one LUT can perform the behavior of 16 flip-flops. Nice savings. The SRL supports clock enable and initialization of its contents. It does not support the use of a set or a reset. So if you code for a set or reset, you'll get a register implementation, and that will waste a good number of registers. So just keep in mind that if you're going to use the SRL, you don't need to use a global reset. The SRL is serial in, serial out. If you code for a parallel read, you will get a register implementation. But experiment with your synthesis tool to determine if it will give you a similar warning of what XST gives you. Of course, that may have changed. That's a little bit old. But still, it kind of points out to you that the warning is often worth reading. Well, we tried to provide a detailed summary of the most important coding tips we provided in this module. To infer the dedicated multiplexer resources, you will need to use a case statement in your HDL and verify with your schematic viewer whether it got inferred correctly. Also note with Muxes, if you plan to break a large multiplexer down into smaller sections in order to pipeline it, be sure to break it into 4:1 and 8:1 Muxes. All 3 control ports can be used on any register, but to directly use the pins, we must make sure we follow the priority of reset, before set, before clock enable. Do not mix asynchronous and synchronous control signals on the same register. We saw a good example of how that can suck up a bunch of LUT inputs. So in effect, it wastes a lot of your logic functionality. So be careful. And continue on with our summary. The SRL does not support set or reset. If you code for a set or reset, again, you'll get a register implementation, not the SRL primitive, and that'll waste registers. The SRL is serial in, serial out, so if you code for a parallel read or write, you'll get a register implementation again. Avoid global resets. If you cannot avoid global asynchronous resets, be aware that also using local synchronous reset will end up wasting LUT inputs. Local synchronous resets create a high fan-out net. That can create timing problems, especially when there is also a global asynchronous reset. So always monitor your control signals and try to manage them. This module introduces some of the architectural differences of Spartan-3 and their impact on HDL coding techniques. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Spartan-3 FPGA. This module also provides some detailed recommendations about creating effective HDL that will provide high speed and reduce the amount of FPGA resources used in your design. After completing this module, you will be able to build an efficient Spartan-3 FPGA design that has an efficient size and runs at high speed. You will also be able to avoid the most common mistakes that new FPGA designers make. This content is essential if you've never coded a design for any 4-input LUT architecture or are converting an ASIC design. Our goal in this module is to take your basic knowledge from the last module and try to teach you some of the subtleties of the Spartan-3 FPGA device. To also teach you to pack the most logic into your FPGA sometimes takes some optimization of your code. Likewise, to get the required design speed sometimes takes further optimization. But often designers do not want or have to follow all the tips provided in this module, but they sometimes will need to. But in the end, we still recommend you probably start with these tips. As you probably know by now, synthesis tools do not allow inference of all FPGA resources. Sometimes good coding techniques are required just to get an optimum resource into your netlist. While the content in this module is not specific to a particular synthesis tool, or for that matter a particular 4-input LUT outside Spartan-3, and some of the tips have not been tested on all synthesis tools, this module does provide a good basis for experimenting with your synthesis tool. Now, this module is recommended content for the Designing for Performance course, as we mentioned. I recommend that you consider taking time to attend the class. And as I mentioned, this content in this module also applies to any 4-input LUT FPGA device family. This includes Vertex 4. There are corresponding RELs on Vertex 5 HDL coding techniques that discuss some of the issues with design conversion and proper coding for a 6-input LUT architecture. We are going to discuss some of the most important ways to optimize your HDL code for a Spartan-3 device. After listening to this entire module, you should be able to make your own checklist of design tips for building a high-speed Spartan-3 design. As you probably already know, the carry chain is used for arithmetic operations. The carry chain can be inferred easily enough by using your standard arithmetic operators. But what you may or may not know is that you cannot infer carry logic when you are using gates, such as the XOR gate to compute a half sum. In this case, the synthesis tool will not be able to infer the carry chain. You should also keep in mind that carry chains do not begin or end halfway through a slice, so it is most efficient to use the carry logic in pairs or an even number of bits. Otherwise, you may end up wasting resources in slices. Most customers don't spend any time comparing the carry logic implementation with other counter types. Using counters of any of these types can save resources or run even faster than a carry logic implementation. While these counters are not used very often, if you are running out of resources or having a timing critical path that passes through a carry chain, you might want to consider one of these other implementations. However, it will take extra time to construct one of these counters in your HDL. Binary counters are slow compared to the others, but requires the least amount of registers. It is also easy to simulate since it has a familiar count sequence. In fact, this is the one type of counter that most likely carry logic will actually be faster than. One-hot encoding is a faster implementation because it has less decode logic and uses more registers as you would expect. One-hot basically activates one register with each count. Johnson counters are ring counters. They are fast and use fewer registers than one-hot encoding, so they do have a bit of an advantage over one-hot. The LFSR counters are also fast and use fewer registers than one-hot encoding. The challenge with the LFSR counters is they use a pseudo-random sequence during the count, so they are harder to simulate and verify. As an FYI, you may want to use the plus and minus signs when building comparators. It will infer a fast implementation. While most synthesis tools don't give you a problem inferring carry logic in this way, you may want to keep in mind that by using these operators, the carry chain is used, and that should be a faster result. Building a decode function using gates can be very efficient and fast if you are using carry logic. The key is describing the decode behavior with an arithmetic operator so the carry logic can be inferred. We will see an example of this in the next slide. The challenge is that it requires a little more work and a bit of imagination to build. Finally, always use a case statement when decoding logic. This tends to synthesize to more of a parallel implementation, or parallel logic as we call it, and tends to run at a higher speed. But keep in mind that even if the logic is built in parallel, a carry logic implementation should be faster. In this implementation, a subtraction was used instead of a LUT implementation. As we mentioned, the benefit is that the carry chain is used and improves the speed of the comparator. As you can see, the greater than and less than signs are too ambiguous since they have to check for all possible conditions. This implies a lot of combinatorial logic since we are comparing two 7-bit buses in this example. But by instead using a simple subtraction, we get a more specific test of the bits on the bus, and this allows us to take advantage of the carry logic resources, which of course has that fast carry chain. The challenge is seeing the opportunity of using a subtraction rather than the old standby if-then behavior description. In this example, we see a decode function built with nested if-then statements. As we know, this infers priority encoders, which synthesizes to extra logic levels and can kill performance. The best solution is to use a case statement which synthesizes to parallel logic. When we implement this decode function, now built with a case statement, the result is fewer levels of logic and better speed. Note that we still use a default statement. This is an important basic HDL coding style to use whenever you build a combinatorial process. This helps you to avoid inferring latches, so to be sure you don't, use a default. Usually synthesis tools will warn you if you happen to forget the use of the default statement. So here are a few things you should remember about coding for the carry logic resources. Be sure to use the proper arithmetic operator to infer carry logic. Don't plan on getting carry logic if you define gates, such as the XOR gate. Consider other counter implementations, especially when you have a timing critical path that goes through an arithmetic function. Okay? And as we mentioned, some of the alternatives include one-hot, and that's probably one of the most commonly used ones, as well as Johnson and LFSR. They'll take extra time to construct, but might save some resources and improve the speed of your design. Consider using and/or or carry logic for decode logic. This will take extra time to construct, but will run faster than a LUT implementation because it will take advantage of the carry chain. Use case statements for decode logic. This will simplify the decoding, saves LUTs, and improves speed. And really the most key thing is improved speeds by tending to synthesize to more parallel logic. And for best density, try to use carry logic in pairs or in an even number of bits. In this example, the top figure we are showing has an input and output register being used. As you know, the IOBs, or the IO blocks, have dedicated registers which provide a fixed input and a fixed output time. These registers are the fastest way to clock data into or out of the FPGA. Timing is simpler because, of course, routing is fixed, and it's easier to predict and control. If you do not use these registers, you end up wasting them. The timing of the IOB registers is fixed and quoted in the databook because there are no programmable routing resources associated within the IOB. You should also know that the DLL, that is the Digital Clock Manager resources, compensates for the clock propagation delay, which improves your I/O timing. All Xilinx devices are equipped with delay lock loops, or DLLs, or digital clock managers, which enable the clock inputs to the device to be conditioned. Although they can be used to multiply the clock frequency and generate multiple clock phases, the most fundamental reason for using them should be to obtain deterministic input and output timing of the device. Make sure you use the DLL to compensate for your clock delay. In this last case, the lower diagram shows the IOB flip-flops not being used. The lower figure will require longer setup and clock-to-output times, since general interconnect will be needed to get the signals to and from the IOBs. Likewise, since we are using general interconnect to route the signals to the registers, the timing will be less predictable. Now, synthesis tools will infer an input ILB flip-flop when a register is inferred if it is directly connected to an input pin and has a fan-in of 1. Likewise, if an output flip-flop is inferred and it has an output of 1 and is directly connected to an output pin, the ILB flip-flop will be used as well. Be sure to double-check with your synthesis tool's schematic viewer that the ILB flip-flops are being used in your design. This slide is reminding you that the slice registers share clocks, clock enables, reset, and set signals. This is important if you want to maximize the number of registers used in your design. You can't just pack any two flip-flops into the same slice for this reason. To improve your device utilization and give the tools the most flexibility to meet your timing needs, we recommend that you reduce the number of clocks in your design and use only one edge of the clock, if possible. Note that the use of the associated set, reset, and clock enable signals with each slice is optional, but the clock signal is not optional. So our best recommendation is to try to reduce the number of clocks in your design so you can improve your device utilization. In this example, we have built a ripple counter, and we want to ask you a couple of questions. What would be the effect of implementing a ripple counter inside of your FPGA? And how many slices do you think this would require? So go ahead and think about this situation a little bit and see if you can determine what is wrong with building a ripple counter inside your FPGA. Well, as you can see, there are simply too many clocks in this design. This would require too many global buffers if you are planning on routing these clocks on the global routing resources. If a customer insisted on doing this, they would probably route the lowest fan-out clocks on general interconnect. Since the fan-out was very low, this would be strongly recommended. But note that either way, none of the flip-flops can be placed into the same slice because the flip-flops don't share the same clock. This would force a poor mapping and waste resources. This may not kill the performance entirely, but it would require you to waste a bunch of half slices. So here is another realistic question. In this design, you're using a simple synchronous reset with a counter. How will your counter implementation be affected if the design also includes a global asynchronous reset signal? So, pause the recording and go ahead and think about that a minute. And in particular, what we're looking at is how do you think this would map the various control signals to the lookup tables? Remember that because you are now using a global asynchronous reset, the flip-flops will be connected to the global reset and a LUT input will be used for the local synchronous reset in this design. This is because the Xilinx Unified Library requires all control ports on a flip-flop to be synchronous or asynchronous, and there's only one reset port on the flip-flop. Since the global reset is asynchronous, this forces all the flip-flops attached to the global reset to be asynchronous. This will also make the global reset a high fan-out net that is routed on general interconnect, and that will result in it having a long routing delay. And hopefully we won't have a routing problem, or for that matter, hopefully we won't have a timing problem. The synchronous reset will now be connected to a LUT input, and this will force a second high fan-out net to be routed, as well as each LUT will lose one input. Try to remember that it's not just the fact you are wasting LUT inputs with the global reset, but that local resets will have to be routed on general interconnect as well, which can be difficult to meet timing. In this example, we also used an additional LUT for the inversion of the synchronous reset and its insertion on the carry chain. This is not a big problem, but does add some delay to the carry chain. With the current polarity of the synchronous reset, the inverter is needed. The inverter could be avoided if the synchronous reset was defined as active low in the code, but this would still not avoid the new critical path completely. So you may not even want to worry about that bit too much. So overall, this design will use more power because the design now routes a global reset net and uses more logic than it might otherwise. Timing may also be harder to meet since the routing in this region is now going to be heavier. So as you probably know by now, global resets are not helpful to getting speed and improving device utilization. Just something to think about. In this example, we built a loadable up-down counter. While this is not difficult to build, you should consider any special connections associated with it. In this case, during a load operation, you have to ignore the feedback of the Q. This means that it has to use an input to the LUT. However, you also have to prevent the feedback from getting back into the carry chain, which is how the mult-and gate helps you out. This allows the count load signal to turn off the feedback of Q when loading in a new value. The inverter is required because during a load operation you must prevent the original Q value from being passed back into the carry logic. But to drive the mult-and correctly, you must put a 0 on the mult-and input when you're loading. To count up and down is the same as adding or subtracting. The key thing to note here is that as your counter gets more functionality, it tends to use more LUT inputs. Now, take this example and in your mind imagine adding a global asynchronous reset and a local reset to the design. And you see that you will quickly add another level of logic and ruin the chance to build a fast counter. So kind of keep this in mind. So here is a summary of some of the coding tips we provided you so far. Take advantage of the ILB resources available to you with the Spartan-3 FPGA. Try to register all of your I/O, and remember that you waste the flip-flops in the ILBs when you don't use them. Do not build ripple counters in FPGAs. Again, they tend to use too many clocks, and those clocks get routed on general interconnect, so you can create some problems that way. Avoid global resets. If you can't avoid a global asynchronous reset, be aware that also using local synchronous resets will end up using more LUTs. So try to manage your overall control signal usage. Local synchronous resets create a high fan-out net, which might create timing problems when there's also a global asynchronous reset. Consider the number of inputs in any special connection, such as a load, that's necessary for more complex functions. They do impact your device utilization because they suck up your LUT inputs. Now, let's go ahead and take a short quiz. Memory is the most fundamental feature of modern FPGAs and is a key element in managing your device cost. It is important to observe the ratio of dedicated memory to logic elements as well as the trend to increase the total quantity of block RAM available. A good FPGA designer must learn how to use and not waste block RAM resources. This slide is logarithmic, so the larger devices are really much larger than they appear here. When you move to a smaller device, the memory to logic ratio increases, so you need to try to use the block RAMs to save the sliced resources. All cost reductions require either removing functionality or optimizing the design and using a smaller device. If you move to a smaller device, the memory to logic ratio increases, so you're probably going to need to be very interested in techniques that use memory to reduce logic requirements. And that's what we're kind of trying to hope to get into in the next few slides. The embedded blocks of RAM provided in the Spartan-3E devices each provide 18 kilobits of RAM or ROM storage. These blocks also have a reasonable degree of flexibility that you can exploit to lower costs. The block RAMs are fully synchronous. Data is written on a clock edge when the write enable is active. Data is read from a given address and transferred to the output on a clock edge. The port enable must be high for any operation to take place. Note that the data output N and data output P ports cannot be tri-stated. The synchronous set and reset port will reset the output register, but an initial value can be specified so that the output can be forced to any value. During a write operation, the output port can become the value that has just been written or the previously stored value at that location. You should also be careful of potential false timing paths caused by the relatively long delay resulting from reading data that has just been written to the block RAM. Each block has two independent ports, including separate clocks. There is no protection against writing to the same location from both ports, but your design should never attempt to do this. So here are a couple good tips. Use the block RAM for logical operations, like any ROM functionality or large combinatorial function. Never infer asynchronous memory into a design. It will use too many additional resources to give it its asynchronous behavior. The 18 kilobit block RAM can be organized in various aspect ratios, that is, words by bits. This means that data can be accessed in the most efficient format for your design. This reduces the logic to format data and eliminates the need for the user to build extra logic to change the data formats. Because the 18K bits are not a power of 2, the aspect ratios have some interesting settings, as you can see from this chart. Only 16K bits are available in the 1, 2, and 4-bit data formats. To make maximum use of the memory available, you can use wider formats, and we encourage you to do so. Don't be afraid of using the parity bit. It is really just another output to the block RAM. There is no dedicated logic to calculate a parity value associated with the block RAM. Note that the 36-bit output configuration prevents access to the dedicated multipliers that are physically located next to each block RAM, and therefore this should be used with care. So basically, keep in mind, if you're going to be going to 36-bit output from block RAM, you may lose access to the particular multiplier placed next to the block RAM. Memory can be inferred in HDL or via the core generator, but to gain the maximum control and tracking of such a valuable resource, it is often a good idea to consider using the Unisim library primitives directly in your code. This is an example of instantiating a Unisim primitive. Also note that if we used the core generator to build this memory, it would also create an instantiation template for you to use. In this case, we are using the 18-bit output of the A port and the 18-bit output of the B port. Note that each port width can be set independently. This is the configurable aspect ratio feature. And here we see an example of connecting a single 18-bit bus to the data and parity bits. The parity bits are just an additional couple of outputs, so there is no reason to keep them separate. The core generator software hides this kind of detail. One of the most important things to remember is that block RAM becomes a ROM if it is never written to. This means that block RAM can be used to replace any LUT function in any design. So in this example, there is a 10-bit address that is used to decode an 18-bit output. Essentially, a large complex decoder is created. Now, when you consider that the equivalent complex functionality would require many LUTs and create multiple levels of logic in the FPGA, this is suddenly a very helpful resource to saving those LUTs and to be able to pack more logic into the FPGA. To encode block RAMs in this way, remember that all the blocks can have their initial contents stored in the configuration bit stream. So upon power-up, every block RAM is programmed. The challenge is writing the initialization string to initialize the 18K bit block RAM. It can get kind of big, and being that it's done in hexadecimal, can be a little challenging. So try to use the block RAM for combinatorial logic. It saves a ton of LUTs. In this example, we have defined the initial values directly into our HDL code. Well, to be fair, this example only shows 4 lines out of the 72 lines that are necessary to initialize a single block RAM. As you can imagine, this is not very popular. In this next example, we have used the core generator to initialize a single block RAM. As you can see, it is not smaller, but it is a little more readable. You should know that if you don't initialize the block RAM, it will come out of configuration with initial contents of 0. So in this case, a reset would not be necessary. This is interesting because if we get in the habit of inferring the appropriate register, we can program the flip-flops to come out of configuration initialized to a particular state without using a global reset. So keep this in mind, because the more resets you avoid building, the more efficient and faster your design will operate. Okay, so now we have an exercise for you to complete. A Spartan-3 device is being used in a cost-critical design where there's a lot of pressure on the resources to fit in the device. The submodule you see here has a requirement for the memory shown. So we've got a 16-bit data in and a 16-bit data out, as well as a 12-bit address port. And we're supposed to accommodate 4K locations. So take a few moments and sketch your solution for the single port RAM for the 4K by 16. we're going to show you how your results can vary depending on the aspect ratios you choose. Again, one of the hidden benefits of using the core generator is that it chooses the best implementation, that is the best input multiplexer logic and output decode logic that is necessary. So this slide shows you the 4K by 16 memory. In this case, the wrong aspect ratio was chosen. Choosing the wrong aspect ratio can waste resources and hurt your timing. In this case, we're building a memory that requires 4 block RAMs. We chose to segment the memory so that only one of the block RAMs was being used at a time, so all 16 bits come from one block RAM at a time. This aspect ratio requires input decode logic, that is the AND gates on the left, and the output Mux logic to be built on the right. This logic, of course, uses extra LUTs and adds input and output delay. In fact, this configuration would require 18 extra slices and get pretty expensive pretty quickly. So keep in mind, if you build this with a core generator, it's going to automatically choose the proper logic and the optimum logic to make this a fast implementation. This slide shows how choosing the correct aspect ratio solves everything. The 1024 by 16 memory is now making use of the internal multiplexing structure of the block RAM blocks so that no other logic is required. In this case, that is with a 4-bit output. So at every sample, each block RAM will contribute 4 bits to the output. This saves you from building any input decode logic. Likewise, the 16-bit output is wired together without any muxing. Block RAM memory can be inferred by a synthesis tool, but it is very unlikely that it would be able to build this. Or, for that matter, would you maybe want to trust it? I don't know. Fortunately, the core generator allows choosing the optimum configuration easy. So in case you start building memories without using the core generator, keep in mind the proper choice of your aspect ratio impacts the speed and the size of your design. Likewise, it's always useful to use spare block RAMs for something, especially if it saves LUTs and improves the speed of your design. The dual port functionality is also a terrific way to access the spare capacity of a block RAM used as a single port memory. This is a question to get you thinking about using block RAM memory in other applications other than as pure RAM and ROM. It may not be the most efficient way to implement a counter, but given the outline of the problem, it is better to use this resource than waste it completely. Remember, it may make it possible to move to a smaller device that has block RAMs, but not enough LUTs. So a design is just too big to fit in the FPGA, and the larger device is too expensive. However, 5 of the 12 block RAMs are unused in this logic-intensive design, and you wonder if they can be used in some way. Then you notice that part of the design requires a set of 10 counters with the following specification. Each counter is a relatively simple 9-bit up-down counter used to indicate an angle in degrees. This is slightly complicated by the fact that the counter has an enable, reset, and saturation logic such that it will not count above 359 degrees or below 0 degrees. So, take a minute and can you outline how the counters can be implemented in the spare block RAMs and make the project meet budgets. A hint for you, a counter is just a special type of state machine. And in the case of you're implementing a state machine, your current state is going to be part of the outputs. So you're going to be feeding back some output bits from the Q output back into the actual address. Okay? So stop the recording and take a few minutes and start to consider how this would be implemented in block RAM. It might actually take you a while. It took me a bit to actually figure this out for the first time. When you're ready to hear the answer, start the recording and you can listen to our solution. The solution for this is very elegant. We can implement the counters by using a single block RAM. We simply have to map out this state machine into an initialization table. We chose a block RAM configured for 2K by 9-bit output. The key is that the state of the counter is encoded as part of the memory location. The 9 bits necessary to encode 360 counter values is encoded as part of the next state address. This next state address is fed back to the address lines from the outputs. You see, this is effectively describing a finite state machine behavior because the next state address, or the next incremental count in this case, is generated as an output and fed back to the inputs of the address port. The only thing left to do is build the enable and reset structure into the block RAM. So as you can see from the table, count up and count down are brought into the memory as one of the 11 inputs to the block RAM. Now the most elegant thing about this construction is that once it's made, it can be used twice. Remember that our original design needed 10 of these counters, but we can make 2 of the counters from one block RAM. That is because the block RAM is dual port and has separate ports. So once a table is used as a ROM, it can be accessed twice. The ROM does not need to be paged if the same contents apply to both ports. One of the concerns is the priority of the control signals. In our case, if the reset is to work, even if the enable is low, then you need to have the additional LUT to resolve this as shown. This design could support an additional control input, the MSB of the address, or you could use this to perform the reset and save the external gate feeding the enable inputs. But this would mean that the enable had to be high for the reset to work, and you could do that with the dedicated SSR pin anyway. You could move the enable to the MSB address, and this would allow the reset to have the highest priority. However, a counter is only a specific state machine. In a normal state machine, you want to maximize on inputs, and hence use the control ports provided. Note that the SSR port can force any value to the output specified by an SR value parameter value. If you had a 32-state state machine, only 5 outputs would define the state. This would leave more inputs and outputs to connect to the system. Although you may engineer the idle state to be zeros, the outputs may need to be a specific value. This is where the SSR value is better than a normal reset. Here is a short list of some of the design tips we just covered about using the block RAM resources. To get the most out of the FPGA, consider converting CLB components into block RAM, especially state machines, large decoders, counter implementations, as we've seen. This is often helpful for designs that are running out of CLB resources and may enable you to move to a smaller device and reduce the cost of your component. Block RAM is synchronous. Also keep in mind the parity bit can be used as an extra output, so don't be afraid to take that output. Choosing an aspect ratio is important for saving resources and good speed, and the core generator will build your large memory with the optimum configuration. Building creative components with the block RAM resources takes extra effort, but it always saves a lot of CLB resources. As I mentioned, finite state machine, counters, and decoders are just some typical applications. Constructing these requires creating an initialization table, which, as I mentioned, is probably the biggest caveat. It's large and it takes a bit of time and effort. But if you've ever done microcoding, you probably won't have too much difficulty. And inferring block RAM has extensive limitations. Most designers like to use the core generator in this case. Now, we wrote a large summary of all the major points we learned in this module. As I mentioned earlier, take advantage of the ILB resources. Don't waste those registers. Minimize the number of clocks in your design, especially in the case if you're trying to think about building a ripple counter or another component that uses a lot of clocks. The more clocks you add, the more congested your routing can come and the tougher it is to meet timing. Use case statements to build decode logic. This simplifies the decoding and saves LUTs and improves speed. Avoid global resets, and we've talked about that a couple of times. Take advantage of carry logic when building decoders. This requires you to build the arithmetic rather than a logic implementation, and it will run faster. Be aware of the number of inputs to your LUTs when you build with a lot of control signals, especially like loadable and up-down counters. Use the best aspect ratio when building block RAM from scratch, or just build it with core generator. To get the most out of the FPGA, consider converting CLB components into block RAM. And we've talked about a number of situations where that could be helpful. Don't forget that. Well, there are lots of places to learn more about FPGAs, and they all start at support.xilinx.com. I want to point out that I referenced several white papers that you might want to check out. They all provide more information on optimizing your design and optimizing the HDL coding for the 4-input LUT. Finally, we spoke about the Xilinx Unified Libraries Guide. It provides insight into the primitives available to designers for each device family. This will explain how to customize the initialization of the block RAM resources and what sizes of block RAM primitives are already available. I recommend you check it out. We also spent a good amount of time talking about the creation of block RAM memories from the core generator. To learn more about this, start the IC tools in CoreGen, select the block RAM memory for customization, and after the GUI opens up, click the Help button. This will open up the block memory generator datasheet. It contains information about device utilization, signals, ports, performance, and the various control options that are embedded within the block RAM resources. Have a look, because the sooner you start using it, the better your results will be. Well, that is it. You have completed the Spartan-3 Coding Techniques modules. There is still more to learn about FPGA design practices, so please consider taking the Essentials of FPGA Design course, formerly known as Fundamentals. Again, my name is Frank Nelson. You've been listening to the Spartan-3 Coding Techniques, Part 2 REL. Thanks for listening.